All right. Good morning. I didn't say it before. My name is Stephanie Paal. I am an associate professor at Texas A&M, so apologies in advance if I do sound like I'm trying to teach a class here. I've gotten that comment before. So today I'm going to talk to you about kind of like a basic application of machine learning that we're doing in my group. This is kind of some of the first work that we did starting out a couple years ago and how it's continued to evolve. I would love to continue to chat about, but basically leveraging machine learning to better understand structural behavior of reinforced concrete components under extreme loads, that extreme load being earthquakes. The goal of all of my work essentially is to use machine learning to understand more, not to understand less. I will emphasize this throughout. There's a lot of applications of machine learning, especially in industry, in terms of like increased efficiency. And we do a little bit of that, or just like a little bit more accurate. But for the most part, we're trying to figure out how can we understand the behavior of something in an area where we don't currently understand it that well. And this is kind of some of the proving ground for that. So we do mostly understand how structures behave under earthquakes, especially reinforced concrete, ductile, non-ductile. But this is the proving ground so that we can kind of extrapolate to other domains. So most of the work that I do, or I would say all of it, is with this goal in mind, to bring the physics base to the data-driven or AI machine learning approaches. So we want to develop these two approaches symbiotically, whether it be the hybridization of those two in one meta model, or like partnering those two in some other way. So you'll see that a little bit in the later part of this presentation. But essentially, the goal of that is because I don't know what's going on. Sorry. Physics-based models, we know, they're governed by physical laws, so that's something that you know to be actually true and then interpretable or explainable. We can say, here's the physics equation that we got from here, or here's what we saw out in the environment, and so that's why we know it to be true, and that makes sense to you, to me. As well as specificity, we're able to design a equation for a specific type of structure, a specific type of material, right? Whereas machine learning approaches, some of the advantages, which maybe I didn't mention before in the last presentation, are this really high accuracy, so we can get a really good prediction for a lot of different data points, as well as computational efficiency, tendency towards real time, which matters in natural hazards, of course, especially when you're talking about reconnaissance, mitigation of the impact, and then generalization capabilities, which is what a lot of my work is focused on, being able to create one model that works for a number of different types of structures or loading mechanisms, etc. And so I said I'm going to talk about seismic performance of reinforced concrete structures. This is a traditional, conventional way to do seismic performance prediction of reinforced concrete structures, and I'm going to get through kind of like the first two parts today in this presentation. So overall, our goal with this work is to be able to understand what's going on for these reinforced concrete buildings. And so I'm going to walk you through kind of the first three of these today, ideally, depending on time. And then the last one, I'll be happy to talk about with anyone anytime. That's kind of what we're working on the day-to-day in my research group at all times. So first off, developing large databases. This is all data-driven. Up until the end, everything you're going to see is only data-driven, and then we bring in some physics. But so we need some sort of large database to base this in. And if you're from the concrete material side, you're going to look at this database, which is experimental data. So on the left, we use pseudostatic cyclic loading, like a pseudo-earthquake load in a lab on a reinforced concrete column to build this data set. You're going to look at this data set maybe and say, if you know anything about AI, this is not big. But it is. There are 422 specimens in this data set, and it is because we're just looking at reinforced concrete columns under this specific loading type. Right? So we've really narrowed it down to be able to understand, what's going on here. And we have a bunch of different splits in terms of like rectangular, circular, different failure mechanisms, as well as different load types, and all of that matters for work later on. But essentially, you can see here, we have 422 reinforced concrete columns. Here now, we're going to try and first predict just what's going on at the component level. And I'm showing you only for columns, but we do this for columns, beams, joints, all the data sets that are available to us, and you'll see that when we get to the system level. We take all of the different input features and then the dependent features. So this is, we're extracting from the hysteretic behavior, and we actually predict the full hysteretic behavior of these columns, which is just like the force deformation relationship, right? If you're not from the earthquake world, I apologize. I see a lot of them are next door, so that's on me. But what's important on the left is that we just have material and design specifications, right? So this is not anything to do with how the load is put on there. We just have like axial load ratio as well as your maximum normalized shear stress, and then just the output response factors. From here, we build an AI model that is able to automatically take that input and correlate it with the output. So we train on like 80% of our data, and then we can test on the remaining 20% of the data. You'll probably see a lot of different machine learning approaches today. So if you want to know why we chose the type of model that we did, I can talk to you about that later. But in these results right here, I'm going to show you the example of a least square support vector machine for regression. So you can see after we've trained and validated that model, we tested on that held out 20% set. And you can see on the bottom right is the machine learning model, as well as up at the top, there are 3 different examples, right? And so then you can see on the bottom is your comparison with ACI in the middle, and says in a mailing, which is a common empirical approach, or not entirely empirical. And then, but yeah, because it's a formula. And then your traditional modeling approaches at the top, so your simulation of that. And you can see in each case at the top, the bright green is the machine learning model, and it just predicts that backbone curve. So these are 4 different parameters this model is predicting, and then down here you just see one of those values. I believe it's the maximum shear in this case, and you can see how if it fits onto that red line, that's the most accurate you can get, right? So we get really good accuracy with these models. We also get a pretty robust performance, meaning that regardless of the holdout set, we get these same results. And so the only issue is that in ACI, like this is intentional, right? Because we want conservative. And so now the next step is like, how can we use these to improve upon that conservative nature, as well as like give this really accurate result some sort of basis in the concrete industry. From there, we moved on to, this is the component level prediction, but for the hysteretic behavior. So in order to get that full hysteretic behavior, that doesn't just come out of a machine learning model, so we had to build 2 different data-driven solvers to get that full time history. And so you can see here for the time history, these results are actually, in my opinion, really beautiful, but you get a really good match between the experiment and the machine learning model on the top in red versus the traditional model, which a lot of times is over-predicting that max value for shear. So again, pretty good results. What's useful here, I think also, is the computational time. So you go from a simulation type approach where you have, this is in seconds, so 1,000 seconds. I should have had my PhD student write that in minutes because it's confusing to me, or hours, but down to 4 seconds. So a really great decrease in time that is needed. So this could be really, really useful if we can bring this to the building level for rapid reconnaissance, being able to figure out, okay, we just know design specifications, material specifications of a structure. How do we automatically identify what the performance is, the max, residual stress? And so here is at the component level a couple of those parameters that are used often in earthquake prediction and reconnaissance. And you can see here again the machine learning model. This is 2 different cases, gets each of those pretty well. There is some error here, but we wanted to figure out, okay, what about if we hybridize this? We are going to use a little bit of physics, and we're going to combine this at the system level so that we can get system level prediction for a couple of buildings, or as many buildings as we had access to. So this approach uses, like your dynamic equilibrium in terms of the physics to constrain this prediction. And then in addition to that, like I said before, we have beams, columns, walls, beam column joints. All of those different data sets are combined together. So we have a model for beam prediction, a model for column prediction, et cetera, and then use all of those together, those machine learning models, to get a prediction on the structural level. So here you see the system level prediction. We have the AI model that defines the parameters at each story. And then here is one of a couple of test specimens that I have results for, but I'll just show one today, of a 3-bay, 3-story reinforced concrete frame, suggested that, now it's quasi-static cyclic loading. So still experimental data. We don't have SHM data at this point. And now you can see a couple of results. So you have your 2-story shear versus your drift ratio for a couple of different locations in this, for your AI model versus your experiment, and then your experiment versus your finite element model, right? And so you can see again, the prediction is very, very accurate. In addition to robust, we get this kind of every time. So I have a bunch of different experiments, but for lack of time, I'm not going to show them. But down here, again, I told you that a lot of the motivation for this is post-earthquake reconnaissance, as well as like any post-disaster reconnaissance. That's kind of where I see the impact mostly, because we're reducing the time from 30 minutes for one of these simulations at the building level to 10 seconds. So we get really accurate prediction in a very fast, a very small computational time. So this last one right here, a lot of my motivation also is to provide these solutions to data-related problems that a lot of you will probably see. So I said data quality is one thing that we're always going to be struggling with until we all get together and solve this issue. And so in my group, we create kind of automated approaches to deal with missing data, extreme values, outlier analysis, etc. And the most important one for me is small data. So in natural hazards, we don't have a lot of information about a load that we've never seen before. So how do we deal with that? And so if you would like to talk to me, I think that we can talk about that. I have a lot of good work in that regard, but I wanted to demonstrate kind of the first base application of this. So you can see here kind of, the motivation was to hybridize these two approaches. In general, I think that's kind of the best path forward. If we can combine physics-based models or physics-based assumptions with these data-driven approaches, I do think we'll get the best of both worlds. You can see down here, we end up with, in this case, some really accurate results. But I do think that if we continue to work in this way, we'll see advances far, far beyond, especially in terms of with these approaches, how do we deal with that small data? If we can get so accurate when we have large amount of data, what can we do when we don't have a lot of data? No approach works for that right now, right? So that's all. Thank you for listening to me for a straight, 40 minutes. I appreciate it.